In this video, I'm going to explain what the limit definition of the derivative is, and how you can use it to find the derivative of a function. So first of all, what is a derivative? Well, a derivative is the instantaneous rate of change at a point. An example of this would be like a speedometer in a car, because it tells you the miles per hour you're traveling at that very instant. So what if we wanted to find the instantaneous rate of change at this point here? One way we can approximate this is through what's called a secant line, which touches the curve at exactly 2 points. When we connect these dots, we get a secant line, which is placed on either side of that red dot, and at its core, the slope of this secant line, m, is going to be what the rate of change actually is. So first of all, we can define slope as y2 minus y1 over x2 minus x1. And when it comes to the limit definition of the derivative, there's actually some fancy ways that this is defined. So first, we're going to call this point on the left x, and then we're going to call the distance between this point and the point on the right h, which means that this point right here is at the x position, x plus h. Similarly, we can define the y value at this point as f of x, and we can define the y value at this point as f of x plus h. Now if we plug this back into our slope formula, we see that y2 is f of x plus h, and y1 is simply f of x, so we subtract these, and then x2 is x plus h, x1 is x, so we will have x plus h minus x. And then this will simplify down to f of x plus h minus f of x on top, and then the two x's cancel, leaving us with this as the slope of our secant line. So this value of m is the average rate of change of the function, but again, what we're trying to find, the derivative, is the instantaneous rate of change. And what you'll actually notice is that as we decrease the distance between these 2 points, the interval of the secant line, we get closer and closer to the actual instantaneous rate of change, which we know is the tangent line at this point and will look something like this. So moving this up here, to actually do this, we are going to take the limit as h approaches 0 of this entire function, which gives us the instantaneous rate of change, or the derivative. This makes sense because again, we established that the distance between these points was h, and here we're trying to find what happens as h, or the interval, approaches 0 and gets infinitely small. Another way you might see the limit definition of the derivative written is the limit as x approaches a of f of x minus f of a over x minus a. And there's just one slight difference between this, and that is that this top limit will actually give you the derivative as a function, and the bottom limit will give you the derivative as a number. Speaking of this idea of the function of a derivative, we actually represent the derivative by f prime of x, which is the derivative of some function f of x. So if you were asked to find what does the derivative of f of x equal, it would be written in this notation. So to see what this is actually going to look like, we're going to try this problem, where we say that given f of x equals x squared, find f prime of x. Find the derivative of f of x. So I'm going to rewrite the limit definition of the derivative right up here, so that we have a starting point, and then I'm just going to go ahead and plug in f of x. So right off the bat, f of x plus h is simply going to be this function f of x, except with x plus h plugged in. So this will provide us with x plus h squared. Then here all we got to do is just insert f of x, which we already know equals x squared. And this is the starting point of our derivative. So from here on out, we're going to simplify this as much as we can. We will get x squared plus 2xh plus h squared, if we FOIL that out, minus x squared all over h. And then here we can start canceling some things out. So x squared and negative x squared cancel out, which will leave us with simply 2xh plus h squared divided by h. Here we are actually going to pull out an h on the top, and when we do this we get h times 2x plus h all divided by h. Then canceling the top and bottom, we are left with the limit as h approaches 0 of 2x plus h. All we got to do now is use the simple plug-in method, and we get 2x plus 0, or 2x. So, erasing this just to clear some room, we get that f prime of x equals 2x. So I hope you guys learned something. Hopefully this very confusing limit definition became a little more clear. And as always, thanks for watching.